All right, everybody, welcome back to the deep dive. So today, we are diving into some pretty mind-bending stuff. We're talking quantum entanglement.
Definitely a topic that I think captures the imagination, even if sometimes it's really hard to wrap your head around it.
Yeah, I mean, you hear quantum entanglement, you probably think a sci-fi movie, right?
Yeah.
Like something out of Star Trek?
Well, it does kind of sound like science fiction, the idea that two particles could be linked no matter how far apart they are, that one can instantly affect the other, like some kind of telepathic connection.
It's like they're having a secret conversation across the universe that we can't even eavesdrop on.
Yeah, and the thing is, it's not science fiction. It's a real phenomenon that's been experimentally proven.
Yeah.
And it's got some pretty profound implications for, well, for our understanding of reality and for future technologies.
Okay, so before we get too far down the rabbit hole here, let's back up and make sure we're all on the same page.
Sure.
What exactly is quantum entanglement? Like, can you give us a definition that even I can understand?
Yeah. All right. So in the simplest terms, quantum entanglement is when two or more particles become linked together in a way that their fates are intertwined no matter how far apart they are. So if you measure the state of one particle, you instantly know the state of the other particle, even if they're light years away.
Okay, so it's like two coins flipped at the same time. If one lands heads, the other one has to be tails.
Right. Yeah, that's a good analogy. But here's where it gets really weird. In the quantum world, the properties of these particles aren't set in stone until you measure them. It's like those coins are spinning in the air, and only when you look at one does it decide to land on heads or tails.
Okay, hold on. So you're saying these particles are in this kind of fuzzy, undecided state until we observe them? And then when we observe one, the other one instantly snaps into the opposite state.
Exactly. And that's what baffled Einstein. He called it spooky action at a distance because it seemed to violate his theory of relativity. Nothing can travel faster than the speed of light. So how could these particles be communicating with each other instantly across vast distances?
Yeah, I mean, that does seem to break the laws of physics as we know them.
Right, and Einstein believed there had to be some hidden variables, some kind of mechanism we weren't seeing that was explaining this apparent faster-than-light communication. But he couldn't prove it.
But then Bell's theorem came along and kind of threw a wrench in things.
Right. Exactly. John Bell, he was a physicist in the 1960s, he came up with this theorem that provided a way to actually test whether Einstein's hidden variables existed. And guess what? When the experiments were carried out, they showed that entanglement was real. There were no hidden variables. This spooky action was the real deal.
Wow, so Einstein was wrong.
Well, let's just say that even the greatest minds can be surprised by the weirdness of quantum mechanics.
Okay, so we've established that this mind-blowing phenomenon actually exists. But how is it being used? Like, what are the real-world applications of this stuff?
Well, one of the most promising applications is in the field of quantum cryptography. You know how important cybersecurity is these days, right?
Yeah, I mean, it seems like every other week we're hearing about some major data breach or hack.
Exactly. And that's where quantum cryptography comes in. It has the potential to create unbreakable codes, making communications super secure.
Unbreakable codes, how does that even work?
Well, because of the unique link between entangled particles, any attempt to intercept a message encoded with entanglement would actually alter the state of the particles. So both the sender and the receiver would instantly know that someone was trying to eavesdrop.
So it's like a self-destructing message.
Exactly. The act of trying to hack it would destroy the information itself.
That's amazing. So you're saying even the most powerful computer in the world couldn't crack a code based on entanglement?
That's the idea. It's like having a lock that changes its key every time someone tries to pick it.
Okay, so quantum cryptography, that's one application. But I've also heard a lot about quantum computing. What exactly is that?
Quantum computers, they leverage this power of entanglement to perform calculations in ways that classical computers just can't.
But what makes them so different from the computers we use every day?
Well, a regular computer uses bits, which can be either a 0 or a 1. But a quantum computer uses qubits, which can be both 0 and 1 at the same time, thanks to, you guessed it, entanglement.
Wait, hold on. So you're saying a qubit can be in two states at once?
Yep. That's another crazy concept from quantum mechanics called superposition. And it's this ability that gives quantum computers the potential to tackle problems that would take classical computers millions of years. Things like simulating complex molecules to design new drugs or optimizing logistics on a global scale.
So it's like they're operating on a whole different level of reality.
Pretty much. And this brings us to what might be the most mind-blowing application of all quantum teleportation.
Okay, now you're really talking my language.
All right.
Are we talking beaming ourselves up like in Star Trek?
Not quite. I mean, we're not talking about teleporting matter, at least not yet. But it's about instantly transferring information. Imagine being able to send data across the globe as quickly as entangled particles influence each other. That's the dream of a quantum internet, all powered by entanglement.
So it's more like teleporting data than teleporting people.
Exactly, but still pretty amazing. And this isn't just theoretical. Back in 2017, Chinese scientists used a satellite called Messias to successfully demonstrate entanglement-based communication over a distance of over 700 miles.
Wow. So all this stuff is actually starting to happen.
Yeah, it's still early days, but the progress is incredibly exciting.
Okay, so I'm getting a sense of the amazing potential of entanglement.
Yeah.
But I have to ask, how do scientists actually create this entanglement in the first place?
Well, it's a very delicate process, usually done in labs, using things like lasers and special crystals to manipulate particles. Think of it like carefully choreographing a dance between two tiny photons. You have to get them into that special entangled state.
So it's a lot harder than just flipping two coins at the same time.
Oh yeah, much harder. And the real challenge isn't just creating entanglement, it's maintaining it. The slightest interference from the environment, like a tiny vibration or change in temperature, what we call decoherence, can break the entanglement. It's like someone bumping into those dancing photons and messing up their routine.
So it's kind of like trying to keep these photons perfectly in sync, even with all this noise and chaos around them.
Exactly. And that's one of the big hurdles we need to overcome if we want to build these quantum technologies and really harness the power of entanglement.
Okay, so we've talked about the practical applications. But I mean, entanglement also raises some pretty big questions about the nature of reality itself, doesn't it?
It definitely does. It challenges our everyday understanding of how the world works, our ideas about locality, that things can only be influenced by their immediate surroundings. Entanglement suggests that there's a much deeper level of interconnectedness in the universe, that things can be linked in ways we never imagined before.
Yeah, it's like the universe is speaking a language that we're just beginning to understand.
Exactly. And some physicists even believe that entanglement could hold clues to solving some of the biggest mysteries in cosmology. Things like the behavior of black holes or even the very origins of the universe.
So we're not just talking about faster computers and unbreakable codes. We're talking about a fundamental shift in how we view the cosmos.
Exactly. And here's something to ponder as we wrap up. If two tiny particles can be connected across vast distances, what other seemingly impossible connections might exist out there in the universe?
Oh, wow. That's a really good question. So much to think about.
Yeah, maybe everything is entangled in ways we haven't even begun to imagine. Who knows what other mysteries the spooky action at a distance might help us unlock?
That's some serious food for thought. It seems like the more we learn about quantum entanglement, the more we realize how much more there is to discover.
Absolutely. It's a journey that's just beginning.
Well, that's all the time we have for today's deep dive. But this is definitely a topic we'll be revisiting. Thanks for listening, everybody, and keep those brains entangled.
Thanks for having me.
See you next time.